These brown pouches hanging on the pegboard are military meals ready to eat, or MREs. Soldiers use these in the field to produce a hot meal without lighting a fire or plugging in a microwave. To understand how a pouch of cold stew heating itself in a forest, we have to move away from the campsite and into the chemistry lab. We are going to recreate Activity 1.4 from the textbook. Our objective is to perform a specific reaction, measure the output, and identify the chemical cause of this heat. By following this setup, we will track how atoms rearrange themselves to generate measurable heat from scratch. We start with a dry glass beaker and a small mound of calcium oxide, also known as quicklime. Before adding the second ingredient, we put on safety goggles and heat-resistant gloves. The textbook warns that adding liquid too quickly can cause a burst of heat that splashes the mixture or shatters the glass beaker. Proper safety gear and a slow, controlled pour protect us from chemical burns during the observation. With the quicklime at the bottom of the beaker, we pour in a steady stream of room-temperature water. This thermometer displays our starting baseline of 22 degrees Celsius. The water reacts immediately. A loud hissing sound begins as the liquid bubbles vigorously around the quicklime. Within seconds, the temperature reading spikes. It races past 40 degrees and continues climbing past the 60-degree mark. The two ingredients have combined to form a single chemical product called calcium hydroxide, or slaked lime. That jump on the thermometer provides the evidence. Forming slaked lime releases a measurable amount of thermal energy. If you were to touch the outside of the beaker right now, with your gloves on, the glass would be hot to the touch. While the bubbling looks like it's boiling over a stove, there is no fire or hidden combustion happening inside the beaker. Without an external heat source, we must find the origin of this sudden burst of energy. This thermal energy is the result of chemical rearrangement, a process that becomes visible once we look at the atoms themselves. Think of the separate atoms of calcium oxide and water as individual Lego bricks. In their separate state, these molecular bricks contain high potential energy. When they mix, they combine. The separate pieces snap together into the single, tightly bound unit of slaked lime. Because this new structure is stable, it requires less internal energy to maintain its shape than the separate pieces did. This diagram shows the excess energy being ejected into the surrounding environment. In chemistry, the prefix exo means out, and thermic means heat. Heat moves out. The heat on the glass of our beaker is the result of chemical bonds snapping together and dumping their unneeded energy. Anytime a chemical reaction forms a product and releases heat, it is classified as an exothermic reaction. You do not need a lab beaker to find these reactions. Your own body runs exothermic processes constantly. During cellular respiration, your body breaks down glucose using oxygen. As those molecules rearrange, they release the energy required to keep you alive. The atomic mechanics that heated our beaker also operate inside your cells to sustain your life.